Good morning. Welcome to Engineering Physics Laboratory. So today we are going to discuss two experiments. The experiment number one is IV characteristics of Zener diode. So what is the aim? In this experiment, our objective is to study the input, nothing but voltage you are giving as an input, and how Zener diode responds as an output, nothing but how the current comes out of the Zener diode experiment. So to study VI characteristics traditionally, or else usually we call it as IV characteristics, anything is fine. So aim is to study and you have to draw your IV curve. To draw IV curve, what is I? Current. Current coming as input or output? Output. So what is V? Voltage you are giving as an input to what? Zener diode. So that is very important. To draw IV curve of, so whenever you are talking, you must write it is a Zener diode, because the property is different to normal diode and the Zener diode. Okay, so don't be lazy, you must write Zener diode. Okay, then apparatus, what you require. So the aim itself says you need to apply voltage, so therefore you must have a, to apply you don't need voltmeter. Voltmeter reads, correct? So the voltage, if you want to read, you need voltmeter. Anyway, you have to know what is the voltmeter. Voltmeter is also required, but you have to apply. How do you apply? Power supply unit. So DC you are saying. You can also take AC. Why we are specified about DC only? Any idea? In this experiment, we take only DC. We don't go AC. Think about it. I will tell you. Battery, in simple language I will write. Right? Then to measure how much you need, voltmeter. Voltmeter reads the voltage. Then current also you want to know. Very good. Ammeter. Then our main hero is Zener diode. That should be there. Then other components. So what are the other? You should know how to connect. So I will be having the battery or DC source here. From the DC source, I have to connect through a resistor. Obviously, it will safeguard my Zener diode. Through a resistor, I am connecting to Zener diode. So what is the symbol of Zener diode? Anyone know? Okay. So at the moment, let me write it like that, Zener diode. Then from Zener diode, you need to connect to the voltmeter, and also you have to connect to the current meter. This is a simple circuit. You have in your book more details. Let us try to understand what is Zener diode for basics. What is the diode means? Louder, louder. Even if it is wrong, it's okay. PN junction. So what do you understand by P? Okay, you have some knowledge about what is P type, what is N type. Okay, very good. So diode is nothing but two terminal device, correct? So basically you are dealing with the semiconductor. What is the beauty of semiconductor is it has two types of charge carriers, all of you know. If you take metal, metal has only metal, or else this is called conductor, no? Metal is nothing but conductor has only electrons as charge carriers. And insulators, insulator has charge carriers, holes, huh? How many of you say it is holes? Insulator charge carriers. Does the insulator conduct electricity? Then where is the charge carrier? Nobody carries the charge. So insulator doesn't have any charge carrier, right? So the beauty of semiconductors here is, so semiconductors is it has electrons as well as holes. Let me represent it with P or H. Anything is fine. In some textbooks H. Okay. So this is a holes. If you prefer H, I'll write that only. Oh, sure. Okay. Holes is positive. Right. Now the semiconductor you can be modulated the way I want. So if I dope more, I'm not going into the details. I can make P type semiconductor. So in the P type, who is more? Electrons are P. Always remember P is nothing but positive, you take like that. Positive. Who is positive here? Holes. So the majority charge carriers, if I say the majority, what happened? Majority is nothing but holes. Cool. And the minority charge carriers are electrons. Always. That's the P type. And the opposite is N type. In the N type, majority capital M is electrons, minority small m is. So either case both are there. Correct. So what we understood, semiconductor is nothing but it has both electron and holes as a charge carriers. No doubt. When I say P type semiconductor, I have majority charge carriers as, and N type has electrons as a majority charge carriers. Okay, with that understanding, now what we do is we will go to normal diode. Let us construct a diode. Diode is nothing but you take one P type. P type has majority. Okay, let me keep more holes. Minority. Agreed? Okay, let me take N type now. If this is my N type has more number of electrons. How many I took there? 4. Okay. Minority has accepted. So diode is nothing but two terminals. Now both of them are sandwiched together like this. That's what we are doing. Take P, take N, sandwich. Cool. So if you sandwich like that, will something happen there? Look at the diagram. Or nothing will happen. Look at the charges. Look at the diagram only. Try to understand. What happens there? What do you see in the diagram? Correct, no? So charges are there. Coulomb forces will play into the action suddenly. So positive charge is positive as well as the negative, but it attracts towards negative charge. Similarly, negative charge is the positive charge ions and it attracts towards negative. So these guy, take one example. The positive charge wants to go to the other side because there is a negative charge. Similarly, from this side, the negative charge wants to go and meet the positive charge in the other region, P region, or else we say it is recombination. Okay, electron hole recombination. Keep it in mind. So there is electron hole pairs we say, or else recombination will happen. Initially they recombine themselves, but after a moment, what happens is they will create their own electric field as a stopping barrier. Nature creates at the surface here, it will create a layer to say stop. Space between them, a potential is formed. This what we say, it is P type, this is N type. There are more number of plus and less number of minus, more number of minus and less number of plus are there, you know. So due to the migration of the charges are depleted in the region and nature will form a barrier on its own due to the recombination of the electron and the holes happen there, and a small voltage is developed in this region. So this region is called depletion region. So the depletion region has a finite electric field or else the voltage, finite electric field. So because now finite electric field you imagine as a gap. Now because the electric field is there, this guy further wants to go other side. He is seeing negative charge, he wants to go other side, but depletion region says because it has finite field is there, it says stop, it won't allow. So though it wants to go, it cannot go. Understand? Now a sort of stability came in the device. So this is how PN junction looks normally, right? So every PN junction, the moment you keep, due to the migration of the charges at the interface of the P and N junction, a depletion layer will be created. It has a typical voltage. Due to that, electrons cannot migrate to the other side. That's how it is protected. It's the beauty of the nature. Okay. So now once you understand this, what is Zener diode? This is normal diode. So normal diode, how do we represent? We represent like this. Correct? Two terminals, terminal 1, terminal 2, two are there. Is it right? You have to draw one line. Now it is right. So which side is P side, which side is N side? This side is positive side, this side is negative side. So because this is positive side, this can be called P region, this is N region. P region is called, which is cathode, which is anode? Which is cathode? P is cathode. N is how? Which can be called cathode? Cathode is something that will attract cations. Cation. Anion. A cation is positive or negative? Cation. Cation is positive. Anion is nothing but negative. Remember, anion is negative. Which can attract negative ions here? This or this? Which will attract negative? P region. So negative, it is attracting negative. So all the negative ions can go there. So it can be called as anode. So please come out of, because the positive is there, okay, it is a cathode. No, because if it is a positive, it is anode, not cathode. And this will be, so N region is your cathode. Even if you ask Viva questions, we ask simple things like this only. Okay, we check your understanding of the subject, cathode and positive. This is a symbol for PN. Now the Zener is, what I will do is, same PN junction I will take and I will dope more number of positives. Here I have shown only 2. For some purpose I need some 10 here. I dope more positives. I dope more negatives. Doping is more, I increase the doping. Therefore, heavily doping makes a Zener diode. Okay. So now what I will do, because I doped and increased my charge carriers more, because it is Zener, I wrote it as a Z. Simple. Okay. Don't use any funny symbols. Slightly Z kind of. Z because it is a Zener. Zener is a name of a scientist. Correct. So again, this is negative side, that side is positive side. Okay. So when we give there, Zener diode we will give, it won't look like this. It may look like some pen, or sometimes like this it will be. Then you should know which side is positive, which side is negative. Okay. Always when Zener diode is given like this, they mark something, some color, yellow or white or black, something, most of the time black. How do we remember which side is positive and negative? This side is black, is negative, no? Common sense. Usually people say, white shirt means, oh, this is a good positive symbol. Okay. Black shirt, if somebody comes, negative guy. Remember at least. Okay, black whenever is there, this is negative side. Nothing but N region, region N. This is P region. Cool. Otherwise, there is another way to recognize, that we will discuss later. Now the Zener diode is given. This is the theorem. All the theory is there. Electron class also they will teach, but learn here. No issues. Right. Now what I have done is, I want to, what is our aim? Somebody tell. To study the, so you need to apply voltage. So take a Zener diode now. Same diagram. From here we will go fast. I have taken a Zener diode. Now I need to connect to battery. Correct. So Zener diode has P type, N type, and a depletion region. This is good. Okay. So here a finite potential is there. So if I want to represent the positives this side, I will keep, negatives this side. So some finite potential is there. Now I want to connect this Zener diode to the battery. How can I connect? This is P side, nothing but here I am seeing positive. N side, here I am seeing negative. That is enough. Now the battery also has 2 terminals. What are they? Positive and negative. Positive is represented with small or big? Big line, and another small line, negative. This is positive, negative. This way I can connect. Somebody says, this girl comes, no, I don't want to connect like that. I will take this terminal. I will connect negative here, positive here, I will connect. Correct, no? Who stops? That also fine. So 2 possibilities are there. You can connect battery either this way or this way. So look, the connection number 1 has your P type of Zener diode is connected to the P type of battery. Correct? So this is called forward. Bias is nothing but if you connect any external electric field to any device, we say it is biased. Understand? Why? The external electric field will dictate us what to do. Sometimes people commonly use, oh, you are biased towards some political party. Nothing but you are already fixed how to think, What to talk? Bias. So the electric field says it will dictate charges. Look, you have to move that side, this side. Because it is dictating us, we say, okay, bias. That's all. If you don't apply an electric field, you never call it as a bias. Understand? So now you are biasing in forward direction. Forward bias is nothing but positive to positive, negative to negative. Other one is positive terminal of the P side is connected to the negative terminal. So it is a reverse biasing option. Right? Now you are applying voltage here. Clear? And what you want to measure, ma? What is your aim? You want to measure current. Okay, let me ask you now, what is the unit of voltage? You know, but you forgot maybe. Very good. V means volts. Okay, don't say V. Tell full name. Volts. Okay, when I say V, always write its units. Never write any physical quantity without units. It is not valid in physics. Okay, and the unit of current is amperes. If it is small, if it is even more small, micro, even nano, pico, you will go like that. Okay, voltage I am applying, I need to measure current, right? So if I don't connect any battery, for example, is any current flowing through the Zener diode? So first I know, okay, I don't connect, I get nothing. Suppose take one condition. What happened here? Take only one condition here. In the forward bias condition I am talking about, forward bias. If I connect DC battery here, suppose I am at some finite voltage, for example 2 volts, let us take. So I am giving some voltage. What happens to the charge carriers here? Look at the charge carriers. One side you concentrate. This is what? Positive. This also positive. Okay. Here what are the charge carriers? Majority. Okay, positive charge carriers. So what happens to the positive charge carriers inside? Repulsion. So they tend to move towards which direction? N type, right? So but do you see any problem there? Somebody is saying don't come. Depletion layer says it won't allow. Correct now? So you have to overcome the depletion layer to move to the other side. That's why you need some push. That's why we connected to the battery. Now because there is a positive charge, here, there is a force of repulsion is seen. Therefore, what happens to the depletion layer? Width of the depletion layer, it was this much width was there before connecting. Once you connected to the forward bias, charges are moving this side also. So what happens to the depletion layer? Decreases. Very, very important point. Okay. So in the forward bias condition, depletion layer is reducing. The width of the depletion layer, what happens? So therefore, reduces. Therefore, is it easy or difficult for a charge to cross over? Easy. So more number of charges can enter into the other region. Therefore, conduction can happen or not. So you can see some finite value of the current. You can see some current. But whereas in the case of no battery, no current. Right. So in the experiment, what we do is you supply current, I mean voltage, and you see how much current is flowing through it. That's all. Very simple experiment. You are going and connecting. Without supplying, nothing is there because gap is there. So the moment you supply little bit 0.1, it will see whether it is sufficient. Look, the charge only moves when it gets a sufficient energy from this to there. Right. Therefore, sometimes you apply 0.3. You may not see because it is not sufficient to overcome. You have to understand why reading not coming, something happened, don't tap. Understand everything has some meaning. Okay, 0.5 I increased, I am not seeing. Understand, okay, the depletion layer is still stopping. Let me push further. Voltage is nothing but you are pushing somebody. Give more electrical energy. Not sufficient. Give little bit more. Wow, current started now. Started going. So nothing but my voltage applied is enough to, you have to understand. So after that you still increase, you will see that current is shooting drastically, nothing but now it increases very rapidly. So you have to slowly increase, don't increase abruptly. Minimum gap, maintain 0.1 or 0.15 like that. Understand? So, but in any case, forward bias don't exceed more than 20 or 30 milliamps. Keep that in mind. for the safety of the Zener diode. Nothing else. Once you see current 20 milliamperes, you stop increasing the voltage. That's all the caution. Now, second option is reverse bias. What happens to the depletion layer in reverse bias? Somebody tell me that. Width of why? Why it increases? Due to therefore, what do you see increases? Depletion layer increases means can the current pass? Can the electron migrate? Or else I want some electron to go outside. What should I do? What should I do? I can't reduce this. You have to push more, right? You have to supply more electrical energy. So in the reverse bias, what you have to observe is, if it is a Zener diode, it should happen theoretically that you are checking in the experimentally. That's it. So verifying something, then you have to feel, wow, it is working. That kind of excitement you have to get. Not simply going taking some reading. So voltage again you are applying in the reverse bias and current you are measuring. So to obtain the voltage, you have to, at 0 anyway it is 0, you have to supply, because gap is more, you have to supply high volt, high. So you have to keep on increasing so much. So high means sometimes depends on the what material I used, how I made the Zener diode. Sometimes it can be 7. Suppose 7 is my Zener voltage. That's how we call it. So when in the reverse bias, if it is a 7, then slowly one guy wants to enter the other side, one electron or the hole. So not too many can go because depletion layer is so much. So very few charge carriers can enter into the other region, or else they participate in the conduction mechanism. Therefore, very few charge carriers are there. Current also will be very, very small compared to forward bias. So in the forward bias itself, if it is milliamperes, what can I expect here? Very good. So I expect definitely my current will be less, micro. Even by mistake, I cannot write there. It's a crime. Agreed? So if somebody is writing milli or simply amperes, I know there is some serious mistake. I can't tolerate this. Okay. So very small current goes even at high voltages. Right? So it starts working at some particular voltage, some value came, you still try to increase further, and again it will increase fast. But what you are doing, how you are connecting the reverse bias? What are the connections? Remember, the positive terminal of the Zener diode. Don't be lazy. Zener diode is connected to negative terminal of the battery. So you are reversed the connections. Therefore, we call it as reverse bias. Similarly, the current is reverse current. So current flows in the system, but it is the reverse current. So always use reverse current whenever you talk about reverse bias. Or else if you say reverse current, people understand, okay, you connected in the reverse bias only. So the reverse current increases fast. When I say reverse, actual the values there you see is positive or negative? Reverse. Positive means normal. When you change the terminals, you should see the negative values. So when I say increases in negative, positively it is decreases, no? So we call reverse current increases. So much value you will observe, 50 microampere something. I say it is increasing. Reverse current is increasing. Basically, it is reducing in the other direction. Right? So in the both the cases, our experiment is done. Both the cases, what we are verifying is we are taking a Zener diode, then we are seeing connect in the forward bias first, simple connection, then you are slowly increasing the voltage. You need some kick to send the electron to the other side, slowly increase the voltage and see how much current is flowing in the forward bias. Once the current reaches 20 milliampere for safe side, you stop the experiment. Enough. Then you connect to the reverse bias, you know how to do it. Simply change the terminals of the battery. If the battery is fixed, change the Zener diode terminals. Anything is fine. Okay. So whatever is feasible there, you do it. You know which is P side, which is N side by looking at it. No need to ask anybody. Yes, no? So once you change it, you should be seeing there reverse voltage, reverse current. Those values you have to plot it. So after this table is there, you have to plot a simple forward diagram. X-axis voltage or current? Because it is independent variable and this is dependent variable. So you can use single graph or two graphs, no issues. To see the overall effect, I will use the single graph. Forward bias, here you see, because it is positive voltage I am applying, positive current I am measuring. So at 0 voltage, you see there is no current, no current, no current, and suddenly some current comes at some point. Maybe forward bias, no, you don't need much. So even before 1 volts you will get, so maybe 0.3 somewhere, then it will shoots very fast. That's how the trend will be. You mark the points like that. Don't draw any line, no issues. So if you want to draw the line, you give the dotted lines. Dotted lines. So now I want to find out in the aim, you did not say, we also want to find out what is knee voltage. Knee voltage is something, the operating voltage. To find out, what you will do is, you take a straight line, extrapolate it to the origin, because it goes, you have to start from there. We don't have points, we say some points are there. So where we have points, here one point, here is there, these many points only we have. So I draw a line connecting all these points. Extrapolation, we say it is extrapolation, right? Extrapolate to the x-axis, wherever it touches the x-axis after extrapolation, that is called knee voltage or threshold voltage in the forward bias. Similarly, in the reverse bias condition, what we do, you need to apply so much current. Okay, at some point of time current shoots up, it will go like this. So it may take 7 or 8 or 9 or 10 or 11, I don't know, you have to see it there. So again same thing, okay, my points are there, extrapolate, okay, touching here, that is called breakdown voltage. So I will ask more details about what is knee voltage, what is breakdown voltage. Lack of time I am not explaining, but it has its own applications. So where do we use Zener diode application? Look at the diagram. Okay, I can use this for some purpose in the reverse bias. If I connect in the forward bias, I can use for this application. So I will give you that exercise. Look at the diagrams. See in electronic equipments where it can be used. That you have to think. Understand? So that's all in the Zener diode experiment. But in the table, while taking the readings, take as many points as possible, as many readings as possible. Understand? 20 means you don't take, don't start with 1 ampere, then go to 10, go to 20 over. Only 3 points you have. Not like that. If you can manage to take 10 readings in between 1 and 20, hats off. 20, even more great. Take as many readings as possible. Look at the current, how the point, maintain the gap between these points. You know, here one point, next point cannot be there. Try to maintain as small as possible. For that, you have to increase the voltage smoothly, as smooth as possible. Understand? Okay. So this is the Zener diode experiment.